This is the screencast for section 4.4, example 2. Here's where it's going to get a little bit tricky as far as the coordinate plane is concerned. We're going to inscribe some rectangles under a different curve. A rectangle is to be inscribed under one arch of the sine curve. So over here you're looking at one arch of the sine curve, and we have a rectangle that has no specific x value. It's just inscribed under the sine curve. What is the largest area the rectangle can have, and what dimensions give that area? Okay, so in other words, like the rectangle could be kind of normal shaped like that. It could be like this. We don't know. It could be really skinny this way. So we don't know exactly where this rectangle is going to be, so we just draw a vague rectangle and pretend we don't know what x coordinate it's going to be on. Now the area of a rectangle is length times width. So I'm going to first try and find an expression for the width of this rectangle. Now, it can't be more than pi, I know that, and it can't be less than 0, but it's pretty hard to find the width of any rectangle. So what I'm going to do is I'm going to look at it in terms of any x value on the x-axis. So if I call this value right here x, the distance between the center of this rectangle and that x value is pi over 2, so this whole pi over 2, minus x. So take out the distance from the y-axis to that x value. So pi over 2 minus x is this little space in here. But we have two of those because that's only to the center of the rectangle. The center of the rectangle is staying in the same spot, so I can easily centralize what I'm measuring off of that. So pi over 2 minus x times 2. Now the height of the side here, height is y coordinate. All of these points are x comma sine of x. No matter whether the rectangle is all the way out here or all the way out here, I take the x coordinate, plug it in, and out comes the y value. So I plug it into sine of x. So the y value here is sine of x. The height of this curve is just going to be sine of x. So the height of the rectangle is going to be sine of x, which means the area of the rectangle is going to be sine of x times 2 times pi over 2 minus x, which you can simplify to be sine of x times pi minus 2x. Alright, so I want to find the largest area this rectangle can have. So I found an expression for the area. Now I need to find the largest. So there's where calculus comes into play. I'm going to take the derivative of the area, and I definitely need to use the product rule here because I have the sine of x function times this pi minus 2x. And this one is getting messy enough where I would definitely consider it a calculator problem. It'd be one thing if this worked out to a beautiful sine or cosine, but this is getting super messy. So I'm going to put that into my calculator, the first derivative as I did it, and get a good window and find its zeros and use this to test. So right here, this is the graph of A prime. This is the graph of A. So you can kind of tell where this maximum of the area is going to be. But again, we can't just do second calc max because that's not using calculus. We've got to use calculus. So I found that the zeros of A prime are 0.710 and 2.431. So then I test that, and I don't need to test. I can just look kind of at the graph here. And I see that there, in fact, is a place where the first derivative changes from positive to negative, meaning the original function will change from increasing to decreasing, and that is at x equals 0.710. Well, that's where x is. That doesn't help me with the height and width of the rectangle. So let's do a couple of things first. We're going to find the largest area by simply plugging in 0.710. So A of 0.710. So this function back up here, the area function, plugging in 0.710, is going to be 1.123 square units. Now to find the actual height and the width, I need to plug in the x value, 0.710, into the width and 0.710 into the height. And I get that the width is 1.722 units and the height is 0.652 units. So basically, in a nutshell, here are all of the answers. The Now Try problem gives us another opportunity to inscribe a rectangle, but this time underneath a triangle. This figure shows a rectangle inscribed in an isosceles right triangle whose hypotenuse is 2 units long. So we need to express the y-coordinate of P in terms of x. And the hint there is write an equation for the line AB. Okay, so this is a This is an isosceles right triangle. I can tell you that this point over here is 1, 0. This point would be -1, 0. So then the question is, what is this up here? With a little trigonometry, this piece of the x-axis down here would be 1. I'm looking for the opposite over adjacent, so the tangent of this over 1 would be 45-degree angle, so this also would be a unit of 1, which means then this point is 0, 1. Now that helps tremendously, and there's the work to show that. So now this line has a y-intercept of 1 and a slope of -1. Turns out that's actually a pretty easy line to write. And that represents the height of any rectangle in here as long as I plug in the x-coordinate. If I take the opposite of that and then add 1, I get the height of any rectangle, no matter if it's here centered on the y-axis, if it's out here centered on the y-axis, it doesn't matter. Part B, express the area of the rectangle in terms of x. So area equals height times width. So we've already got the height, that y-coordinate we came up with. Now we just need the width. So again, our rectangle is centered, but this time on the y-axis, so I don't actually need that. I'm looking for the distance from the y-axis, which is x. Depending on what x I plug in, it's still going to be the x-coordinate. So the rectangle, luckily enough, is just twice the distance from the y-axis to that x-coordinate, so 2x. So the area is going to be that -x plus 1 and then times 2x. Part C, what is the largest area the rectangle can have and what are its dimensions? So I know that I can do second calc maximum and find it, but that wouldn't be using calculus. So I'm going to take the first derivative of our area function, find its zeros, and test them on a number line. And I get that there is that maximum that I predicted at 1/2 because A prime changes from positive to negative, so A changes from increasing to decreasing. So that 1/2 just gives me the x-coordinate that I need to plug in. The actual area I have to plug in to the 1/2 to the area formula, so A of 1/2 is going to be 1/2 of a square unit. And that means that the height is going to be 1/2, which then I can predict that the width would be 1. 2 times 1/2 is in fact 1 unit. So I have the total area and the dimensions of the inscribed triangle that has the largest area.